Well, hello, wonderful students. All right, so quiz 409 talks about the fundamental theorem of algebra. So depending on when you watch this, we haven't had class yet. So I love class with you guys because you ask those great questions. You have those wonderful observations. But so I'm just going to kind of be direct. If you have follow-up questions, you can always reach out, all right? Fundamental theorem of algebra. It sounds pretty intense, right? Oof, this is a big one. Well, let's take a look and see if you have any patterns. How many complex roots does the polynomial equation have? How am I supposed to know? Well, they said the answer is 4. Huh. -3, 4, power minus 7x, 4, 7 times 4, plus 17 equals 0. Well, that's 28. 4 to the 4th power is, oh my gosh, 64 times 4. 224? No, that's 4 times 4 times 4 times 4. 256 times -3. Oops. 256 times -3. 256 times -3. On my calculator, you have to use the negative, not the minus. So I got an error. -196,608. There's no way 4 makes it equal to 0. Huh. Wait a minute. There's a 4 right there, though. There's a 3 there, and 3 is the answer for that one. There's a 5 right there. The degree of the polynomial. Let's see. So if the answer is 5, we might be onto something. Oh, it is. So if you're not familiar with the fundamental theorem of algebra, it is the observation that the number of solutions, values of x, that will make a polynomial equal to 0 among the complex numbers, so not necessarily real numbers, which we'll talk about in a second, is going to be equal to the degree of the polynomial. Let's think back to Unit 2. If we had x to the 5th, right, and we took the 5th root to solve that, right, the 5th root, well, x to the 5th is the same as x times x times x times x times x. So yes, it's the same number in this example. It's the same exact solution 5 times. We call that the multiplicity would then be 5 at this example for this point in time. But there's 5 x's that are possible solutions to the 5th root, right? A solution there. So that's a very, very generalized explanation just to explain what this word complex roots comes from. I had to do some research because it didn't pop in my brain that roots, radicals, and undoing the degree is where that came from. So complex solutions might be a more comfortable word. Basically, it's values of x that when we substitute them in, will make the equation equal to 0. Why does it say complex? Also, back in Unit 2, we were introduced to our best friend, the imaginary number. Well, with this new discovery, invention, whatever you want to think about it, the imaginary number, which is actually equal to the square root of -1, the square root of -1 doesn't represent anything physical, anything real in our life. I'm sorry, I forgot this was fun. So that's why we call it an imaginary number, because it has an imaginary relationship to the world around us, but it's got a real value, which is this, it's got a defined value of the square root of -1. At that point, we're given complex numbers, where we have the real part, meaning a real number a, plus b times I, where I is, again, the square root of -1. We've just defined it as that because negative square roots, negative even roots don't make sense mathematically. but they pop up. We suddenly have the use for imaginary numbers in the sciences. Ask Mr. Spurlock and see how they're applied there. So these are called complex numbers. Very briefly, let's think about this. If poodles, I had a teacup poodle for 13 and a half years. Her name was Bala. She was the best dog on the planet. A dog, right? If poodles are a subset of dogs, real numbers, meaning all the numbers without the letter I, we call them the reals, are actually a subset of complex numbers. We talked briefly about this logic when we were first introduced. So the complex numbers encompass even more kinds of numbers than the reals because they have this BI. The reals, the reason they're contained inside the complex numbers, because all of the real numbers are captured when b equals 0. So it's still a complex number. The number, how about the number 21? The number 21 is still a complex number, hence a complex root. It's a real root because just the real part is left, but it could be written as 21 plus 0 I. That's why it is considered a subset, right? Poodles are still dogs, right? No matter if it's a tiny poodle or a big poodle or a labradoodle, it's still a dog. Same thing here. So the real numbers are still complex numbers. They're just where I has a 0 for a coefficient. So that's what's happening here for the fundamental theorem of algebra. It says that the degree of your polynomial is how many complex roots you will have. So what does that mean? We'll talk about that some more. So if we're just to use it right now for the way you're going to be assessed, look at the highest degree of your polynomial. And if they ask you how many complex roots does the polynomial have, say 5. Say 3. Say 4. It just says it must. They might repeat. They might be complex or imaginary. Or they might be real, meaning actual real x-intercepts. So we'll talk about that. And when they repeat, what does that mean when they repeat? We'll talk about that in a second. Multiplicity. Okay. Let's go on. Which answer best describes the complex zeros of the polynomial function? Okay, so we're getting into thinking in theory. Like, how would this apply? When would this happen? And how do we use, we haven't done anything. I'm going to go graph it, though. I want to graph it. But what do we do? Well, we need to think about the fundamental theorem of algebra. Well, according to the fundamental theorem of algebra, there's going to be 3 complex zeros, 3 complex roots, 3 complex solutions. Some of them could be real numbers with no I. Some of them could be repeated, and I'll show you what I mean. Remember when like x times x. And then some of them could be real, or I think I already said that, complex, meaning we won't see them on a graph. On our regular graphing calculator, we won't see them because they're in the complex plane. They're in that graph where the reals are the x-axis and I don't remember if the real is the x-axis and the imaginaries, the i's are the y-axis. So don't quote me on that, but we change it. It's a different plane. It's no longer the coordinate plane with xy plane, right? It's the imaginary plane. So, all right, let's go graph it. Enough of this so we can make some sense of it. We talked about this tool. If you're not familiar, get familiar, reach out to me for support, ask any questions you have, watch tutorials. Look, a student just showed me, what's this little question mark do? Look at that, it has help right there. So click on that or reach out to me, that's fine. All right, I'm gonna make this exponents because it doesn't copy paste correctly. So you have to have technology skills to make it work. All right, now we need another skill. Look, it looks like a line. It's just a line? That doesn't make any sense. The graph, where the graph is. Depending on where you zoom into the graph or zoom out of the graph will change the way it looks. It won't change key features. which is why the algebraic method, we're thinking about just the general relationship of how different parts of the polynomial affect a graph. The highest degree is 3, so it's a cubic function. The leading coefficient is positive, so I know that the end behavior is going to do like some sort of loop, loopity-loop, and I know it's going to go up as we go to the right, and it's going to go down as we go to the left. Okay, it's going to look something like that. Furthermore, if x was 0, 0, 0, I know the y-intercept is going to be at -6. So that's helpful, just key features of the graph. And I'm going to stop there at that point. That's what I can see right now without doing any more math. Just not factoring, not nothing, just by looking at the key features of the polynomial. Okay. I'm going to zoom out. Oh, look at it. Okay. This is a very tiny, teeny, tiny curve. It looks very straight, but watch if I click there, there is the y-intercept. Well, according to the fundamental theorem of algebra, there should be 3 complex roots. If they were real roots, they would be crossing the x-axis. But how many times does it cross the x-axis? Well, just once. Okay, so that could still be the entire real root if there's a multiplicity of 3. What does that mean? I don't like this anymore, but I guess it's going to stay there. Whatever, those are going to stay there. Okay. Remember some of our other theorems. If positive 1 is a 0, then f of 1 equals 0, which means x minus 1 is a factor. So let me write that. X minus 1 is a factor. But according to the fundamental theorem of algebra, there needs to be 3 complex roots or solutions. This is what multiplicity means. What if I just wrote that 3 times for now? Oh, there's a parabola. Look how it changes. I'm going to write it one more time. Ah, it's close, but it's not exactly the same graph. It's bothering me. I normally use the other one, so sorry, guys. I use my draw on page, but I like how this stays. So I might switch to this pen tool because I like that it stayed on the screen when I was done. So anyway, right here, I was checking multiplicity of the real root, meaning the real actual x-intercept right here. It's going to be the same for the blue graph and for the red graph. We are more concerned with the red graph. So let me turn off the blue graph for now. Look, it still has a real x-intercept, a real 0 at x equals 1. But according to the fundamental theorem of algebra, either this is repeated 3 times, which is what I wrote over here, or it's going to have 2 complex roots, meaning they're in the complex plane. We can't see them, but they're there. So that's kind of the use of the fundamental theorem of algebra. It helps us know that we have other solutions out there in maybe the imaginary realm, but they're still very useful and you're getting exposure to them. Just try your best. Try your best, okay? Let's talk about multiplicity. This curve and this curve, the graphs are not the same. You can see that, right? We're going to zoom in. Wow, it's wild. It looks almost like a straight line, right? This blue line has a degree of 3. It has 3 real roots. All of the roots are at x equal 1. All of the solutions where the graph equals 0, where the function equals 0, is at x equal 1. We just call the multiplicity 3 because it's repeated. This is what I'm talking about with repeated roots. Yes, it's still the same number. It's just 1. But the way that it factors, you can either see it like that or you could write it. Any guesses? Any guesses? Any guesses? Maybe I should have written it out here. We'll do another graph. That's exactly the same. Don't worry about the red graph right now. So the green graph will match the blue graph. Right? I'll turn off the red graph. So that's just a understanding what multiplicity means, repeated roots, like repeated zeros, what that means, and then how to identify using the fundamental theorem of algebra whether or not you have a multiplicity of a root, let's see, or if you have a complex roots. Okay? So you can always check that to see what's going on here. Another thing, a key detail is, let's take a look at this. See how with a multiplicity of 3, see how it kind of goes flat and then crosses? That's kind of a visual feature that you kind of need. This one is like straight across, like boop, boop, right? So for those, it's once. It's a 1 times 0. So it goes boop, boop, straight across. Let's see if I can do a different example really quick, just for the thinking purposes, because this is hard. I made 2 long videos last year to support students, so you can fast forward as needed. Okay, notice this is only got 1. It only has 1 0 at x equals 4, but it's repeated. It's repeated twice. When it's an even multiplicity, it's just going to touch and then go back up. That's how you know that one's even. Okay? If you have remember how we said just once? If it's just a multiplicity of 1, meaning it's just 1, 0, 1 root, it just goes boop, boop, straight across. Boop, boop, straight across. If it's got an even multiplicity, right, I'm going to make this squared, and this black graph is going to be a curve. It's going to come down and touch and go back up. Watch. So it's going to be a cubic function now, raised to the power of 2. Aha, see at 5, it's got an even, let me turn off this graph, an even multiplicity. It's a cubic function, so we need 3 roots. Notice it crosses directly at x equals 1, so we know it's x minus 1. It comes down and touches and comes back up at x equals 5, so we know it's a real root at x equals 5 with a multiplicity of 2. So hopefully that's starting to help you visually use the graph to help you determine the types of roots using all of your theorems. And then now with the fundamental theorem of algebra, thinking about it like that. Okay, so multiplicity of 1, it goes straight across. An even multiplicity, meaning a repeated root, comes down and touches, right? The squared. So it's a cubic function, still has 3 complex roots. It has 1, and it has 5, and 5. Okay, so that's those. This one shows you an odd multiplicity. So it's got 3 real roots that are repeated. And look at what it does. It comes up, it kind of hugs really close, and then it goes back up. That lets you know there's an odd number of repeated roots. That's the x minus 1 3 times, right? The green graph is the same. It's the x minus 1 repeated 3 times. And then finally, the fundamental theorem of algebra states this has 3 complex roots. This goes directly straight across, right? Straight across, so that has 1. That's only 1 root. So therefore, it has to have 2 complex roots. We'll talk about that in a second. There's no other x-intercepts. It's an odd degree function, so we know it's not going to suddenly curve back down. This is going to keep going up. This is going to keep going down. So it has, let's look at the answers. We're looking for 1 real root and 2 complex roots in the description. The function has 1 real 0 and 2 non-real zeros. That's fine. 2 imaginary numbered zeros. Because it intersects the x-axis at exactly 1 location. Not only does it intersect at only 1 location, it just goes straight across. It doesn't do that little hug, implying a multiplicity. All right, that's just question 2. Let's keep going. Save mouse. What does that mean? I don't know what that means. How many complex roots does this equation have? What's the highest degree? What's the highest degree? 0 equals 2x cubed minus 4x squared minus x plus 1. They just put the 0 in front on the left-hand side of the equal sign. That doesn't matter. The equal sign, it doesn't matter. You just know if this is the equal sign, whatever's on this side has to equal to this side. Well, according to this, we're using the theorem. Hopefully you said 3. Okay? So no matter which variation you have, check it. Okay? Look for that pattern. Look for that pattern, okay? Look at the highest degree of your polynomial and try it. Ooh, what is the completely factored form of x cubed plus 4x squared plus 7x plus 6? Strategies we've had, look, factor by grouping. We did that in Unit 3. We did some of it, here and there. Definitely in Unit 3. I don't see a friendly factor or greatest common factor. I don't see a way to regroup this. Nope. Factor by grouping won't work. Now we have the rational root theorem, so we can just try a couple of values to see if we plug them into f of, let's say, 6, and see if it equals 0. You can do that. If it does, then x minus 6, is a factor. You could try 1 to see, no, they're all positive. 1 plus 4 plus 7, no, that's not going to work. You could try negative 1. Anyway, I don't think that works either. No. Okay. Those are always potential rational roots. At this point, because we don't have any other information, well, now we do. We're going to graph it. I want to use graphs because that's kind of a focus. We know there's going to be 3 roots. They might be complex. They might be real. Let's go find out. Maybe. Let's go find out. There we go. There we go. Control copy. Desmos. Let's get rid of these. Boop, 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 boop. Well, that didn't work. Control copy. Control V. What is going on? What do we do when that happens? I don't know. Let's try one more time. One more time. I'm going to right click, copy, right click. Okay, it worked that time. I don't know what was happening there. Maybe a tech error on my part. Shift 6, make it an exponent because we need it to be exactly the right form. There I just deleted it and did Shift 6. X cubed plus 4x squared plus 7x plus 6. They need to match. Practice typing it out. It's an important skill, especially since it's not going away. The technology is not going away. Okay, I'm kind of zooming in. I'm going to adjust the bounds here just because I want to. I'm going to shrink my face. X goes to -5, and let's just go to 2 because it doesn't look like in a step of 1. Let's go, that's fine. We can maybe go to -10 and +10 and see what happens. Goes up pretty, yeah. See how it doesn't, let's see, not a little, like you just fixed the bounds. Well, I changed my mind. Okay, so here's our graph. What would you say? Do you say this? Let's zoom in there. All right, let me stop. Fundamental theorem of algebra says there's going to be 3 complex roots. So either we're going to be able to factor this into 3 nice parentheses or somehow write this, or we're not. And we still can, but we're going to get a complex root, so we're going to talk about that. All right. Why did I choose graphing instead of like the rational root theorem and plug and chugging and trying to figure out a factor? Well, this is faster. Remember, this is saying that x equals -2 is a 0. I'm going to still use my traditional one. So according to the factor theorem, f of -2 equals 0. So we know that x minus -2 is a factor, right? F of a, if f of a equals 0, x minus a is a factor. So in this case, we know that x plus 2, a double negative, negative minus negative 2 makes it actually plus 2. Minus a minus makes it a positive. When they're double negatives, it makes it a positive, right? Don't, never is the double negative in English. So we know that this is a factor. Let me show you x plus 2. That's a line, but look, it crosses right there at the same place as the green graph. Now we just need to figure out what the other parentheses are. Right? Clearly it's not just these regular x's. Oh, look, there's a 0 there. We don't want that. So something is happening. We'll notice the green graph, let me turn off this purple graph, doesn't touch the x-axis again. It doesn't really hug. Like it kind of just, no, I wouldn't say it like whoop, hugs the graph. Let's turn this one on. Look right here. Look how that hugs the graph. Or, oh no, this is a multiplicity of 2. So no, it actually like comes down, touches, and goes back up. But if this was a multiplicity of 3, we'll see that hug that I'm talking about. Okay, see? So if negative 2 was repeated 3 times, see how it hugs the graph, crosses, and goes up. So we know this is not fully factored form and really no version of it, meaning no other numbers, maybe because there's like a 7x and a 4x, nothing else in here is going to change it. Yeah, it's not going to, okay, this one just completely crosses. Oh yeah, because they're all different now. They're not repeated. Okay, I'm getting rid of that. Let's talk about the green one. Again, that looks like it just kind of crosses straight over. So that probably has and does have a multiplicity of 1. So we know x plus 2 is a factor, but we don't know the other ones. We've got to try to figure those out. At that point, we use synthetic division. We do. We use synthetic division to factor it to a quadratic. That was kind of one of the uses of the theorems. So here we go. I'm just going to stay here. Synthetic division says, I'm going to divide by this. But remember, it was f of negative 2. That's the value. So that's going to be my divisor. Okay, that's the 0. That's the root. Then I'm going to list all my coefficients. There's a 1, a 4, a 7, a 6. Draw my line. This is an algorithm. Synthetic division is a process by which we can divide polynomials following these steps. How they work and why they work is a different kind of question. Like, why does baking soda make things rise? Why do we need butter or oil in cookie recipes but not water or milk or like a liquid, right? The why behind it, I'm not sure in a baking recipe. Here, we could talk about it a little bit more in detail. But for now, I want you guys just to focus on the steps, following steps. It's a great place to practice in math class because we can just see, can I follow these steps? Make sure you understand the vocabulary. There's an invisible 1, that coefficient. We don't write it, so we know if there's just a variable and there's nothing in front of it, there is an invisible 1. Then there's a 4, the 7, and the 6. So that's the first step. Next, we bring this number straight down under the line we drew. This is the setup. The next part, we just repeat. We'll multiply, add, multiply, add, multiply, add until we're done. The other step for synthetic division is to make sure you do the step down correctly, meaning if this x squared term was gone, if it wasn't there, we would have put a 0 as a placeholder, representing a 0x squared. Yet other invisible math, but it is what it is. So let's those are just the key overview. For this problem, we have it set up correctly. Let's follow the steps. Multiply. Negative 2 times 1. Write it under the next number. That's negative 2. Add. 4 minus 2 or 4 plus negative 2 is positive 2. Start over. Multiply. Negative 2 times 2, negative 4. Add. 7 plus negative 4 or 7 minus 4, they're the same, is positive 3. Multiply. Negative 2 times 3 is negative 6. Add. 6 plus negative 6 or 6 minus 6 is 0. That's perfect. In synthetic division, one of the final ideas is this last number will always be the value of your remainder, always. We want the remainder to be equal 0 based on the factor theorem, based on what we discovered. Otherwise, we did something wrong. We wanted the remainder to be 0 based on the remainder theorem, the factor theorem. That is a factor, therefore the remainder should be 0. Okay? How does this help us? Well, now we can write a quadratic. We can write the quadratic version, which I'll type right here. We'll still factor it because it wants it in fully factored form. Okay, for synthetic division, if your dividend was a cubic, your quotient, your answer, will be a step down. So if it's cubic, it's going to be quadratic. If it's to the power of 3, it's going to be to the power of 2. So then you replace your variables in the same order, x squared, then x, and then that's your constant. So we divided by this, x plus 2. We got our new polynomial, which is x squared plus 2x plus 3. Please remember that. X squared, right, plus 2x plus 3. Aha! Oh, whoa, let me turn it on. Okay, phew. Let's change this color. Let's change it to blue. Okay, so look, the blue and the green graph are exactly the same. But we're not quite done because this is a quadratic equation and we got lots of rules, lots of tools, lots of tips and tricks for factoring a quadratic equation. So we're not fully factored. Let's graph just that quadratic for now, okay? Please let me know if you have any questions. It's hard, right? We used a graph to figure out a zero, a root, a solution. We used the factor theorem to write that as a factor, x plus 2. We then use synthetic division to figure out the other polynomial, the leftover polynomial, to factor it. And look how they're exactly the same. I'm going to turn these two off for a second and just talk about this one, because now we want to factor that one, and we can do the same steps. Let's graph it, look for any zeros or roots. Uh-oh. I knew this was going to happen. That's why I wanted to do it. Does this parabola cross the x-axis at all? No. Does this parabola have any value on this graph of x that will make it equal 0? Will this ever equal 0? No. It will not. It will never equal 0. That is as low as it'll get. That's the minimum right there. 2 is the minimum value, the minimum output value, the y value that this function, this parabola, will ever reach. What does that mean? Well, according to the fundamental theorem of algebra, there are 2 complex roots, 2 values of x that make this equal to 0. And you guessed it, it's actually in the, they're non-real, they're imaginary, they're in the complex numbers. So how do we find that? You have some options. I guess you could complete the square if you want. That would still give you the answer for complex roots. I'm going to use the quadratic formula. Why not? The quadratic formula will never let you down, okay? It will never, ever let you down. It is the opposite of b, plus and minus. No, let me find the right. Now, so we'll have to do 2 separate ones. We'll do plus the square root plus the square root of b squared minus 4ac, all of that over 2 times a. Okay, so that is the quadratic formula. And you're like, why are you typing it in here? Well, I'm going to show you because I'm being lazy today. You are welcome to use this calculator, okay, plus or minus. That's what the or means. You're going to get 2 solutions, which brings me to the next part about the fundamental theorem of algebra. So if at any point this gets too long, just feel free to pause it and start again. That's the beautiful thing about videos. There are always going to be 2 complex roots if you have complex roots, always. And this is why. Because you'll always have the plus and the minus version of the squaring, the square root. If you remember, when we were solving things like x squared is equal to 9, we take the square root of both sides. We take the square root of both sides because we have to undo the square, so we get just x. Well, x is actually equal to 3, yes, but it's equal to plus or minus 3. It's not the same thing as I because the plus and minus sign is on the outside of the square root function. All it's telling us is if you have a negative times a negative, it becomes a positive. So if you have positive 3 times positive 3, that's 9. But so is negative 3 times negative 3. That's also 9. So if you have a complex root, then you're going to have a complex pair. We call it a complex conjugate. So you'll have the plus and minus right there by the square root, by the I. You'll have the plus I minus I. Okay? All right, that's just, what are we going to do here? Let's add a slider for all of them. We'll do this down here at the bottom. It says it's undefined. Let me move you over here. So down here, I'm going to put in the values. This is, again, how do we read a quadratic equation to plug it into the quadratic formula? If you remember, the coefficient A is for the quadratic term, the leading term. So A is going to be equal to 1. So I'm going to scroll down. A is equal to 1. Cool. B is the coefficient of the x term, the linear term. So that's 2. I'm going to make that 2. 2? What? Oh, it's going to be undefined. This won't work for us anyway. So B is 2, right? A is 1. It's not going to work. I'll replace it in here. And then 3 is C. So let's go down and make 3 equal to C. It's going to still be undefined. Oh boy, how come it's going to be undefined? So we'll have to do this math the old-fashioned way. I forgot. It's undefined because it is a imaginary number. It has the letter I, and Desmos doesn't calculate with I. And neither do some of my other calculators that I share with students. Only one does, so far that I have seen, has the capability of computing complex roots. So we're going to have to do this by hand. There's the beautiful quadratic formula. Let's go ahead and pull this up. Let's make this a little bit darker. Okay, we've already identified A, B, and C, so now we need to do plug and chug. B is, opposite of B is negative 2. I'm going to do just the plus one. This might help you guys if you do one at a time. Maybe, maybe not. All right, so we'll do 2 squared minus 4 times 1 times 3. All over 2 times 1. I'm going to put the plus or minus. That's just saying I'm going to add whatever this square root is, and I'm going to subtract whatever that square root is. That's all it's saying. 2 different answers. All right, now let's simplify. Looks like right here I have 4 minus 12. The square root of 4 minus 12. This is just 2. So what is that equal to? The 4 minus 12 is the square root of negative 8. There's our undefined portion right there. There it is. Okay, so now let's write it down here. Negative 2 plus or minus the square root of negative 8 all over 2. It just means each part is being divided by 2. Okay? All right, what do we do next? We got to get rid of that negative. And if you were here, if you remember the negative square root, do you remember? You can rewrite it like this. Negative 2 plus and minus I, square root of just 8. Whenever you have a negative square root, pull out the negative and put it as the letter I, the imaginary number, in front. That's why they were created. That's why they defined it as I is equal to the square root of -1. Although that over 2, we're not done. They want you to simplify. So now we have to look at this 8 and think, can we simplify that radical? We can. 8 is 4 times 2, and the square root of 4 is 2, so we can still write this. We're not done. We can still write this as -2 plus and minus. Let me just show you that real quick. Square root of 8 is equal to the square root of 4 times the square root of 2. Properties of radicals. Well, the square root of 4 is just 2, so now we'll have 2i times root 2. Okay, unit 2 all divided by 2. Aha! We're still not done. We can still simplify because of this denominator, this division by 2. This whole thing will simplify. This 2 divided by 2 is 1. 2 divided by 2 is 1. So now, over here, instead of saying undefined, we should have 1 that says 1 plus I root 2. The 2's canceled. The 2's divided out. And down here, instead of saying undefined, we should have 1 minus I root 2. I don't think I can show you that graphically because we're not there yet, technology, which is why it's so new, even for you guys, for me, why it may seem so difficult, that letter I. It's relatively new. It's a relatively new concept in mathematics. Let's go see how we did. 1, okay, x plus 2, parentheses, 1 plus I root 2, 1 minus I root 2. Oh, and the x. Oh gosh, the x. I forgot about the x. See this? X minus that whole quantity, x plus that whole quantity. Oh boy, that's factoring over the complex numbers again. It is very difficult. It's okay. So let's try it. Let's see if maybe this one's a little bit friendlier. I think it is. Can you factor by grouping? Let's try it. Factor by grouping. I'm going to group this one. I'm going to group this one. I see 4s. I see 16. I see x squareds. I want to try it. This first grouping, I'm going to pull out an x squared. I'll get x squared. X minus 4 is left. Cool. Plus, the second grouping, I'm going to pull out a 4. X minus 16 is left. No. Check my work. X minus 4 is left. So those are matching. These two are left. So it'll factor as x squared plus 4x squared. X minus 4. Cool. All good things. Notice this, for this to equal 0, set them equal to 0. That's another way to factor. It's another way to find these. We don't have to graph it because you won't see the answers under the graph. All right, so we know x minus 4 when x equals 4. Check, that works. What about this one? We can fully factor this one like we saw earlier. We just need to also set it equal to 0. You could use the quadratic formula. You can do all sorts of things here, but this will help us factor. Let's subtract 4 from both sides. So that will become x squared is equal to -4. Take the square root of both sides. Here we'll get the plus or minus I times the square root of 4, right? And x squared, the square root of x squared is just x. Wait a minute, the square root of 4 is just 2. But whenever we write that, we always put the I in front of the radical, but we put whole numbers or real numbers in front of the I. Truly, they're the same. It's just notation. Cool. So now, what does that mean? How would we write it? Well, x minus 4 is a factor. But now, so is it if x equals plus 2i, right? So we'd have minus 2i, because when we plug in positive 2i, that'll cancel. nx plus 2i, because when we plug in negative 2i, it'll cancel. Okay. Factoring over the complex numbers was hard. It was the last lesson in Unit 3. It is the last lesson here in Unit 4. So just keep thinking and trying, applying anything that you do understand, breaking the problem down into smaller parts. Thank you for watching. I hope this is helpful. If it is not, don't use it. If it is, pause it, rewind it, ask me questions, give me tips and tricks for improving. Thank you again. I'll talk to you guys later.